What is Braess paradox? Well, Braess paradox, credited to the German mathematician Dietrich Braess, states that adding extra capacity to a network when the moving entities selfishly choose their route can in some cases reduce overall performance. But what does this mean? Well, let's look at it. I'm going to break it down for you in simple terms so you can kind of get what it's all about. So first, let's try to think of a metaphor. Imagine a road network, such a network that you would be driving cars and, just an actual road connecting places. So, we have a car, right? So, it's not just this car, it's actually more cars. Not more cars, a lot of cars. Let's say 400 for this example. Here we have a diagram, but we're going to put it in terms where you can understand. Lowercase t means time traveled. Uppercase T means amount of cars, divided by 100. So right here, we have a start point and an end point. We have two routes you can take. You could take either route A, which is on top of the screen, or you can take route B, which is the bottom. Let's look at route A first. Route A, first half of route A, has t equaling uppercase T divided by 100. So t for this instance would be 400 divided by 100, which is 40. The second half of route A is a set 45 minutes. Bottom half, route B, on the left hand side, t equals a standard set 45 minutes. But on the right side, the right half of route B is going to be t equals capital T divided by 100, which is again is going to be 40. For this example, we're going to imagine that there is no route between A and B, and only options A and B are optional. So here you can see cars can only go two routes, and both routes equal 85 minutes total from start to end. This is what we like to think as Nash equilibrium. Definition of Nash equilibrium is a solution concept of a non-cooperative game involving two or more players in which each player is assumed to know the equilibrium strategies of the other players, and no player has anything to gain by changing only his own strategy alternatively. So what does this all mean? Let me try to break it down to an example. I'm going to use a battleship as an example. Here we have one ship, on the opposite side another. These two ships are in battle. First ship launches a rocket at the second ship. But let's just assume that the second ship knows every move that the first ship is going to make and vice versa. So the first ship, knowing that the second ship, knowing that the first ship is going to shoot a rocket, shoots a rocket in the exact same space, and that is its strategy, which works because the two rockets meet and collide in air and nobody gets hurt. First ship does the same thing, shoots another rocket. Second ship counters. First ship again. Then the second ship again. This would go on forever. The two ships understand that this is the case, so they both surrender. This is an example of what we call Nash equilibrium. So let's get back to our diagram here. Now that you have a better understanding of what Nash equilibrium is, let's take a look and see what Braess paradox would mean to this diagram. So say we have more cars on the street, but we actually open up the route between A and B. This route is very fast. For this example, we'll say it's 0.1 hours. a huge significance in travel time. So the optimal route would be the first half of A, which equals 45 minutes, the route from A to B, which is a fraction of an hour, then route B to the end, which is 40 minutes. This is faster than any route A or B, which totals 85 minutes. But as we see cars using route A and B, it does not make it faster. It actually does the opposite and clutters everything up. When people are given options to selfishly take a faster route, Braess paradox states that this can decrease performance instead of increasing performance. As you can see here, the clutter of everything involved makes everything worse. So how does this come to be involved with computers? Well, instead of cars, let's imagine that it's binary code instead. So let's transverse these cars into binary code. All this binary code gets sent to the computer. Just as if we had the diagram for the cars, we can show the same diagram that represents binary code in computers. So again, we're sending the cars into binary code, and now binary code gets sent into the computer, telling the computer what to do. So let's look at this binary code. As it goes along and starts into the program, we see that if it is allowed to have multiple options, this is not going to actually increase performance, but Braess theory states that it will do the exact opposite and decrease performance. So as information gets sent into the computer, if it does not have a set route to go and selfishly takes the faster route, we can see a dilemma where Braess states that this will decrease performance. As we can see, instead of optimal straight flow of binary code, we're getting just bits and pieces because of the clutterness that has happened between the start and the end of the process. This is due because of the extra route between A and B in this figure. Now, as we see, the scattered binary code travels through the computer. This represents a decrease in performance. So now that we know Braess paradox, we can further look into deep depth about how this reacts with our everyday life as IT professionals. Thank you for your time, and I hope you enjoyed.